You know, in the kind of weird and wonderful world of two-dimensional quantum physics, there's this single mysterious number. It's like a universal fingerprint for an entire theory, and it tells us pretty much everything, from how complex it is to how it actually bends to the will of space-time itself. This number is called the central charge, or just C, and today we're going to pull back the curtain and figure out what it's all about.
So just imagine for a second, what if you could take an entire quantum field theory, all of its particles, all of its forces, all the ways they interact, and boil it all down into one single value. A value that just tells you how much stuff is really in it, how rich and complex it is. What would that number even be? Well, in the world of 2D conformal field theories, that number is C.
All right, so here's our game plan. We're going to start at the very mathematical heart of the theory to see where C is born. Then we'll see how it shows up in the real world as an actual physical force. We'll even look at how it plays with the curvature of spacetime, helps us count quantum states, and finally reveals this deep, irreversible law of nature. It's going to be a wild ride.
Okay, first things first. To find C, we've got to look at the master blueprint of our quantum world. It's this thing called the stress-energy tensor. The easiest way to think about it is as a guide that tells us where all the energy and momentum is at any given point. It's basically the core rulebook for how everything moves and interacts. So, physicists had this really clever idea. They asked, what happens when you take two of these master blueprints, these stress-energy tensors, and you smush them really, really close together? There's a mathematical tool for this called an operator product expansion. And when you run the numbers, something really weird happens. As they get closer, the math kind of spits out the tensors themselves, but it also spits out this brand new piece, a simple number that just appears out of nowhere. And that new term is directly tied to a constant number, which we just label C. And that, right there, is the central charge. See, it's not something we just made up. It emerges right out of the fundamental rules of the theory. It's like a constant of nature, but just for this specific little quantum world. So, the big question is, what does this number actually mean? Well, it turns out C is basically a counter. It's counting the number of fundamental building blocks, or degrees of freedom, in the theory. So a really simple theory that just describes one type of particle might have C equals 1. A more complicated one with, say, 10 types of particles could have a central charge of 10. It literally measures the amount of quantum stuff in the system.
Okay, so C is this number that just pops out of the math. But what does it actually do? Well, this is where it gets cool. It turns out this very abstract number can actually show up as a real physical force, and it all depends on your point of view.
Now, when physicists change their coordinate systems, like stretching or squeezing their perspective, most things transform in a nice, predictable way. But the stress-energy tensor, it's a bit of a rebel. Its transformation rule has this bizarre extra mathematical piece tacked on, and right out front, leading the charge, is our number C. This is a huge clue. C is the thing that governs how the theory's energy and momentum react when you start messing with their container.
Let's actually see this in action. Imagine our 2D world is just a flat sheet of paper. Simple enough, right? Now, what happens if we roll that paper up into a cylinder? You'd think, so what? Nothing really changes. But in the quantum world, because of that strange transformation rule involving C, the vacuum of empty space itself actually notices. It reacts to this change in shape.
And get this. Here's the consequence. Just by rolling the plane into a cylinder, you create a negative energy in the vacuum. This is a real, measurable force known as the Casimir effect, which can actually push surfaces together. And the strength of this force? It is directly proportional to the central charge. A bigger C means a stronger force. All of a sudden, our abstract number is creating a very, very real push.
So, the central charge doesn't just respond to us rolling up spacetime. It also responds to spacetime's own built-in curvature, and this leads to one of its most profound consequences, something called the Weil anomaly. Classically, a conformal theory is what we call scale invariant. That just means the physics looks the same whether you zoom way in or zoom way out, even on a curved surface. But in the quantum world, that's just not quite true. The quantum vacuum is this bubbling, active place, and it absolutely notices the curvature of the stage it's living on.
And this effect has a name, the Weil anomaly. Basically, a certain quantity that should be zero in the classical theory, the trace of the stress-energy tensor, suddenly isn't zero anymore when you put the quantum theory on a curved background. the theory's perfect scale invariance is broken.
And guess what determines the size of this anomaly? How much the symmetry is broken. You got it. It's our number, c, multiplied by a measure of spacetime's curvature. I mean, this is profound. C acts like a bridge, telling us exactly how strongly the quantum fields in a theory react to the geometry they live in. It's how much they feel the effects of gravity.
So far, we've seen C measure complexity and dictate physical forces, but it has another incredible trick up its sleeve. It can count. Specifically, it can help us figure out the entropy of a system, which is really just a measure of its information content.
Okay, so imagine heating our quantum system up to an insanely high temperature. There's going to be an absolutely enormous number of possible quantum states the system could find itself in. The logarithm of that number is what we call entropy. But how on earth could we possibly count all of those states? It seems impossible.
Well, this is where a truly stunning result called Cardy's formula comes into play. It gives us a direct recipe. The entropy at high energy is tied to the square root of the energy and the central charge. Think about that. This one number c that we found just hiding in the math also tells us the total information content of the entire system. It connects the theory's deep structure to its statistical soul.
And that brings us to the final, and maybe the most profound, property of the central charge. It provides a fundamental law, almost like an arrow of time, for how physical theories can evolve from one to another. This is known as Zhemelo-Chekhov C-theorem.
So, in physics, a really common thing to do is to study a system by zooming out. We start with a really complicated high-energy theory, what physicists call the ultraviolet or UV theory. Then we kind of average over all the tiny, fussy details to get a simpler, more effective theory that works at lower energies, the infrared or IR theory. This whole process is called renormalization group flow.
And the C-theorem gives us a simple, unbreakable rule for this whole process. The central charge of the high-energy theory you start with, CUV, has to always be greater than or equal to the central charge of the low-energy theory you end up with, CIR.
This rule is just huge. It means that as you zoom out from any physical system, you can only ever lose complexity. You can never just spontaneously gain it. The flow from complex to simple is a one-way street. And since C is our measure of information in the theory, this means information is lost in our description as we zoom out. It gives us a fundamental arrow of time, not for the universe, but for the space of all possible physical theories.
And this leaves us with this really deep and fascinating puzzle. We're often told that in fundamental quantum mechanics, information is never truly lost. But the C-theorem guarantees that our descriptions of the universe must shed information as we zoom out to larger scales. So, what does this clash between a fundamental law and our effective descriptions actually tell us about the ultimate nature of reality? It's a powerful question, and it just shows you how deep this one little number c really goes.